It's a very interesting worded question. It says solve each equation below line. I think that this was supposed to be a period, and this line is not supposed to be here, so that's a typo. So solve each equation below. There's a part A and a part B. Let's go ahead and look at part A first. So if you're having someone who's helping you with these, let's just say if you've got someone who's pretty good at math and they're helping you as a tutor, be careful because if they ask you questions like, is your teacher talking to you about logarithms or natural logs or different bases? Just say no. We're not dealing with logarithms. That's a tool that we'll look at in Math 3, and you'll be able to solve these in different manners then. And right now these are kind of pretty narrowly constructed because we have to be able to manipulate these so that we can get the same bases. So you might just say Mr. Roberts said something about getting the bases to be the same. And for this problem, if I look at it, there's a special, with the number 2, there's something going on here. So for example, if I look at 2 to the first power, that is 2. 2 to the second power is the number 4. 2 to the third is 8, right? And I can keep going this way. 2 to the fourth is 16. But I can also go backwards. So 2 to the 0 power, we already know that's 1, right? Anything to the 0 power is 1. But 2 to the negative 1 power is the number 1/2. Now, the reason why I point this out is that this 1/2, right, is the same as 2 to the negative 1 power. And also this number 4, right? This number 4 here is the same as 2 squared. So what we're going to do is we're going to replace the 1/2 with 2 to the negative 1 power because they're equal to each other. And we're going to replace the 4 with 2 to the second power because 2 to the second power is the same thing as 4. When we do that, we're going to construct a situation where we have the same bases. And if we have two expressions that have equal bases, the only way that they can be equal to each other is if their exponents are equal. So again, this is pretty narrowly constructed, and there's not a lot of variations on these problems we can do, but always try and get the bases to be the same and think about what, base 2 numbers look like. So I'm going to rewrite this. Instead of writing 4 to the x power, I'm going to write 2 squared, and then that gets raised to the x power. So if you look real closely here, what I'm doing is I'm just replacing, right? This thing I've highlighted in blue is the same thing as it was blue up above, right? So all I have here is 4 to the x power. It's exactly the same. And then on the other side of that equal symbol, we're going to write, instead of 1/2, we're going to write 2 to the negative 1 power, and then we're going to raise that to the x minus 9 power. And again, if you look closely, this 2 to the negative 1 power is exactly the same thing as 1/2. Now, when you have a power raised to a power, right? And we can go back and look at something like, hey, if I have a to the b to the c power, right? Laws of exponents tell us that that's the same thing as a to the b times c power, right? And we've looked at a lot of numerical examples of that, but at this point I just want to, put out this one law of exponents and just kind of use it because I'm going to transform this by just doing this multiplication, right? So instead of 2 squared to the x power, I'm just going to write this as 2 to the 2x power. On the other side, I'm going to write it as 2, and then I'm going to very carefully multiply -1. Let me move this over a bit. -1 times x minus 9. So I am going to multiply these two exponents. I'm going to multiply the -1 times x minus 9. But you notice I've got to distribute that to both of those. So it becomes 2 to the negative x power and then plus 9. So this is super nice now because I have the exact same basis, right? It's 2 to some power equals 2 to some power. The only way this is possible is if the exponents are the same. In other words, if this is the same as this. And that's the final step in our strategy. We're just going to set those equal to each other. So I'm going to write, hey, 2x equals the opposite of x plus 9. If I add x to each side, I get that 3x is 9, therefore x has to be the number 3. So when x is 3, right, the left and right hand side of the original equation they become the same, and it's kind of a large number. It's 4 times 4 is 16 times 4 is, I don't know, 64 or something like that. Okay, so that's part A. And again, the strategy here is to get the bases the same. I know 4 is a power of 2. I know 1/2 is, a power of 2. So I just kind of looked at these different powers of 2 until I could get, things that were equivalent to what I had. All right, so let's take a look at part B. So in part B, probably my best option here is to use fraction busters, right? And if you look at it, if I want to eliminate these fractions, the thing that I probably almost always would do is multiply both sides of this equation, both sides, by x. In fact, I'll go ahead and write it as x over 1, x over 1. So, if I look at this right-hand side, when I multiply this x over 1 times x plus 5 over x, you can see I end up with an x in the numerator and an x in the denominator. So there's a giant 1 there. I have to do that twice on the other side, right? I have to multiply this x and this x will match up. So those will form a giant 1. Over here, there's not going to be a giant 1, so I'm just going to have 2 times x. But this has to be multiplied both of these terms. So if I look at it on the left-hand side, because I've got an x in the numerator and an x in the denominator. In fact, let me write that out. This is going to be I'll just write the steps so maybe you can see it a little bit better. This would be an x times x plus 3 over an x, and then plus 2 times x. And that will equal, on the other side, x plus 5 times an x over an x. So I hope you can see where I do have the giant 1, right? X over x is a 1, and x over x is 1. They're factors in their numerator and denominator. They're common factors, so they form a giant 1. So if I simplify this by eliminating the giant 1s, I end up with, whoops, black pen.